last class, we were discussing design of one-way slab. I explained to you what is one-way and two-way slab. However, there were some corrections in the earlier calculations. So therefore, we will revisit all the calculations that we have done in the last class. Okay, Tanisha?
Yes, sir.
Okay. So design of one-way slab, we were designing this example, design and one-way slab of span 4 meter carrying floor finish load of 1.5 kilonewton per meter square and imposed load of 5 kilonewton per meter square. Consider the slab as simply supported at edges. And I have drawn the diagram below. Are you able to see the diagram?
Yes, sir.
Uh, so if you look at this diagram, uh, there are beams at two opposite edges. Can you see those beams?
Yes, sir.
Yeah. And the slab is spanning between these two beams. There are no beams all around the slab. There are beams only at the opposite edges. So the slab is going to, if I have to draw the bend shape of the slab, it is going to bend in this fashion. So it is going to bend only in one direction. It is not going to bend in this direction. Are you with me?
Yes, sir.
So therefore we call it as one-way slab. And how do we design one-way slab? One-way slab is considered to be the strip of 1 meter wide slabs placed one after the other. So if you look at the diagram here, I have shown this 1 meter in red color. So consider a strip of 1 meter width, hmm, and thickness equal to thickness of slab. And let us consider that n number of such strips are placed one after the other. Are you with me?
Yes, sir.
Okay. So now what we are going to do is we are going to design this strip. So let me mark that strip's cross-sectional area here. So I am marking this. So this is a strip of width 1 meter and thickness is equal to thickness of slab. Are you with me?
Yes, sir.
Okay. So if I look at this slab from this view, so let me call it as view XX. So how does that view XX look like? So this is view XX. Are you with me?
Yes, sir.
Ah. So you see the two beams at the edges and there is a slab which is resting on these two beams. And the span of the slab, that is the distance between the two beams, is 4 meter. Are you with me?
Yes, sir.
Okay. So what is the first step? The first step in design of any slab, either it is one-way slab or two-way slab, is calculation of slab's effective depth by giving consideration to something called as L by D ratio, where L is the span of the slab. So what is L in our case? In our case, the span of the slab is 4 meter. Are you with me?
Yes, sir.
Okay. Now, as per IS code, if beam or slab is cantilever, this L by D ratio which is allowed should be less than 7. If the beam or slab is simply supported, the allowable L by D ratio is less than 20. And if the beam or slab is continuous, the allowed L by D ratio is less than 26. Are you with me?
Yes, sir.
Okay, so in our case, it has been given in the problem statement that this slab is simply supported over these two beams and therefore our L by D ratio allowable is 20. So our L by D ratio should be equal to 20 or less than 20. Are you with me?
Yes, sir.
Ah, so in our case, L is 4000 mm. So D required will be 4000 divided by this 20. So that turns out to be 200 mm. And now we are going to calculate capital D. So in last class, I have already explained how to calculate this capital D to again give the glimpse of that. If I draw the cross section of the slab, it looks something like this. The slab has reinforcement running in both directions. So this is the reinforcement running perpendicular to the plane of paper. Are you with me?
Yes, sir.
And this is the reinforcement which runs in the direction of the paper. So what do? We have to find out effective depth. So if I draw the zoomed view of this is the reinforcement running parallel to the plane of paper and this is the reinforcement running perpendicular to the plane of paper. So we have to compute this up to the center of this reinforcement distance from top of the slab. That needs to be calculated as D. Are you with me?
Yes.
And in yesterday's class, I explained you that will be 200 mm. That is the effective depth which is required. So capital D overall depth will be 200 plus 1.5 times bar diameter in mm plus 25 mm, which is clear cover. So that is 200 plus 1.5 into 12 plus 25 equal to 250 mm. This we have discussed at length in last class. Do you remember that?
Yes, sir.
Okay, now let us do the load calculation. The load calculation will involve uh, the self weight of slab, and so let me write down that. So the first thing is self weight of slab. Are you with me?
Yes, sir.
Self weight of slab. And how are we going to do this load calculation? So look at this sketch. We have to design this slab as a beam of width 1 meter and depth equal to overall depth of slab. Are you able to imagine that?
Yes.
Now I have to calculate load per meter run on this beam. So I have to calculate the UDL intensity on this beam. So what do? I consider 1 meter length in the span direction, and already in other direction we have 1 meter length. So what is the area of this chunk? It is 1 meter by 1 meter. Happy?
Yes, sir.
And we compute all the loads on this 1 meter by 1 meter chunk, and that will be considered as the UDL acting on the slab. So what is the volume of this chunk? So if you look at this chunk, its volume will be 1 meter into 1 meter into this overall depth of the slab, isn't it?
Yes, sir.
I want to compute the volume of this chunk. So that turns out to be 1 meter into 1 meter into D. So self weight of the slab, I have to write it as 1 meter into 1 meter into depth, overall depth in meter, that is 0.25. And what is the self weight of reinforced concrete? Self weight of reinforced concrete is 25 kilonewton per meter cube. Are you with me?
Yes, sir.
So it is 1 into 1 into 0.25 into 25. That turns out to be 6.25. And this load is load per meter run. So therefore it is 6.25 kilonewton per meter. Are you with me?
Yes, sir.
Okay. Now let us compute the load due to floor finish or dead load. So for that, I have to consider a chunk of 1 meter by 1 meter. So floor finish load is already given in the problem statement as 1.5 kilonewton per meter square. So the load will be 1.5 kilonewton per meter square into 1, which is 1.5 kilonewton per meter. Are you with me?
Yes, sir.
Okay. And now let us consider the imposed load. So imposed load in the problem statement is given as 5 kilonewton per meter square. So what will be the load on this 1 meter by 1 meter chunk? So 5 kilonewton per meter square into 1 meter into 1 meter. That turns out to be 5 kilonewton. But that But you have to understand that this is the load only on 1 meter chunk in this direction. So this load will keep on repeating all along the span. So this load is in UDL, kilonewton per meter. Are you with me?
Yes, sir.
Okay. So what is the total unfactored UDL? It is this 5, which is imposed load, plus 1.5, which is floor finish, plus 6.25, which is dead load. So that is 12.75 kilonewton per meter. Are you with me?
Yes, sir.
Now, what is the total factored UDL? The factored UDL is represented by notation WU. That factored UDL will be this 12.75 multiplied by 1.5, which is partial safety factor for load. That turns out to be 19.125 kilonewton per meter. Happy?
Yes, sir.
So now let me draw the loading diagram. So you have two beams at the ends, and the UDL that we have calculated is 19.125 kilonewton per meter. Now let me draw the shear force diagram. To calculate the shear force diagram, I will have to calculate the reactions. owing to the symmetry of the load, reaction will be total load by 2. So look at this 19.125 kilonewton per meter multiplied by 4 meter. This is in mm. So you have to convert it into meter. So 19.125 into 4. This is the total load divided by 2. Are you with me?
Yes, sir.
Okay, so that reaction turns out to be 38.25 kilonewton, and this reaction also will be 38.25 kilonewton. So the shear force diagram looks like this: rise by the reaction, fall linearly, and then rise by the reaction. So this is 38.25, 38.25, and this occurs at exactly the mid span, that is 2 meter and 2 meter. Are you with me?
Yes, sir.
So at mid span, the shear force is 0, and it linearly increases towards supports. At both the supports, the shear force value will be 38.25. Positive or negative, that doesn't matter. Are you with me?
Yes, sir.
Okay, now for which shear force are we going to check this slab? We are not going to check this slab or design this slab for the shear force, highest value of shear force. Why? Because I have told you that the crack in shear initiates at 45°, and whenever this crack reaches the top surface, then only the sliding can occur along this inclined surface under the shear force acting at distance d. Are you with me?
Yes, sir.
So I have to compute now shear force at distance d. But what is distance d? D is effective depth, and we have already calculated the effective depth as 200 mm, that is 0.2 meter. Are you with me?
Yes, sir.
So we have to compute the shear force at distance 0.2 meter from this support. Happy?
Yes, sir.
Ah, So now go distance 2, you go distance 2 from here. So if you go distance of 2 meters from here, you get the shear force of 38.25. So if you go this much distance, so how much is that distance? 2 meter minus 0.2, that is 1.8 meter. Are you with me?
Yes, sir.
So this distance is 1.8 meter. So it's similarity of triangles, or in simple in Marathi त्याला त्रैराशिक असं म्हणतात, इंग्लिश मध्ये क्रॉस मल्टिप्लिकेशन म्हणतात. So go distance 2, you get 38.25. Go distance 1.8 from here. What is the shear force that you get? What is the value of this shear force? Are you with me?
Yes, sir.
So that will be 1.8 divided by 2 into 38.25. That is approximately equal to 33.46 kilonewton. Happy?
Yes, sir.
So we are going to design or check this slab for shear force is equal to VUD. U stands for ultimate, D stands for design. Ultimate design shear force of 33.46 kilonewton. Are you with me?
Yes, sir.
And now we also need to find out what is the maximum bending moment for which this slab needs to be designed. The maximum bending moment for simply supported beam loaded with UDL over entire span happens at the mid span, that is at 2 meter from the left end. And how much is the value? WL square by 8. But what is the value of W? We have calculated the value of W as 19.125, isn't it?
Yes, sir.
So 19.125, I took it as 125, 25. It's okay. 19.125 into 4 square by 8. That value turns out to be close to 38.5 kilonewton meter. Are you with me?
Yes, sir.
हाँ तो 19.125 लेना चाहिए था, वो मैंने 19.25 लिया है. सो थोड़ी सी ये वैल्यू गलत होगी, बट इट्स ऑल राइट, इट्स नॉट टू ऑफ. आर यू विथ मी?
Yes, sir.
So we are going to design, check this slab for shear force is equal to 33.46 kilonewton. Just a minute. अरे इथे डिस्कस करू नका, लेक्चर झालं. 33.46 kilonewton and MUD equal to 38.5 kilonewton meter. Are you with me?
Yes, sir.
So what is the next step in slab design? Next step in slab design is calculation of area of steel. And we are considering that, let us say that we are going to use M20 concrete and FE 500 concrete. Are you with me?
Yes, sir.
So M20 means we are going to use a concrete which has characteristic compressive strength of 20 MPa, and Fe 500 grade steel means the one which has characteristic tensile strength of 500 MPa. Happy?
Yes, sir.
So first of all, to calculate AST, we have to prove that this section is under reinforced section. So how do we do that? So we are going to calculate moment of resistance of balanced section with the provided effective depth. So that will be RUB into B into D square, where D is the effective depth of slab. RUB for M20 and Fe 500, we have to calculate that value is 2.66. We know that. So 2.66 into BD square. But what is the width of the slab? So we are considering it to be a strip of 1000 mm width and thickness of effective thickness or effective depth of 200 mm. Are you with me?
Yes, sir.
So B value is 1000, D value is 200. So RUB into 1000 into 200 square, that is 2.66 into 1000 into 200 square. That turns out to be 106.4 into 10 power 6 Newton mm, which converts to kilonewton meter as 106.4 kilonewton meter. Are you with me?
Yes, sir.
So देखो balance section का moment of resistance is greater than the design moment that this slab has to resist. So therefore this slab is going to require steel lesser than that is required for balance section, and therefore the section is under reinforced. Are you with me?
Yes, sir.
फिर से एक बार आर्ग्यूमेंट देखो. बैलेंस सेक्शन का मोमेंट ऑफ रेजिस्टेंस है 106.4 एंड डिजाइन मोमेंट है यहाँ पे 38.5. सो नेचुरली फॉर 38.5 kilonewton meter you will require lesser steel than 106.4 kilonewton meter, isn't it?
Yes, sir.
So if you are providing steel less than that is provided for balance section, the section is under reinforced. Are you with me?
Yes, sir.
Therefore, this section is under reinforced, and now we can use the formula that I gave for calculation of AST use for under reinforced section, and that formula is 0.5 into FCK upon Fy into bracket 1 minus square root of 1 minus 4.6 MUD upon FCK BD square into BD. Are you with me?
Yes, sir.
So let us substitute these values here. So 0.5 into FCK, that is 20 upon 500, that is Fy into bracket 1 minus square root of 1 minus 4.6. Now the quotient here MUD is to be substituted in Newton mm. So I am substituting MUD has to be substituted in which unit? Newton and mm. Are you with me?
Yes, sir.
So in this formula, you have to substitute forces in Newton, lengths in mm. That care needs to be taken. So 1 minus square root of 1 minus 4.6 into 38.5. This is in kilonewton meter. But what is that value in Newton mm then? Kilonewton to Newton conversion is 10 power 3. Meter to mm conversion is 10 power 3. So total 10 power 6. Are you with me?
Yes, sir.
So 1 minus 4.6 into 38.5 into 10 power 6 upon FCK is 20. B is 1000, width of the strip of slab which we are designing, and D square, that is 200 square. Happy?
Yes, sir.
So 4.6 into 38.5 into 10 power 6 divided by 20 into 1000 into 200 square. The bracket complete, and outside में क्या है? B into D. So what is B? 1000. What is D? 200. Are you with me?
Yes, sir.
So if you calculate this value turns out to be 470.41 mm square. Happy?
Yes, sir.
So what does that mean? You have to provide a steel of 470 mm. 470 mm in which direction? So देखो, if I look at this strip, let me draw the drawing of this strip here. So how is this strip? This strip is of 1000 meter, 1000 mm, that is 1 meter wide. Are you with me? And this depth is 250 mm. So 0.25 meter. Happy?
Sir.
How does this strip bend? it bends in this direction, like this. Happy?
Yes, sir.
So in this view, if I were to draw the bending, it bends in this direction, like this. Happy?
Yes, sir.
So how do you provide the reinforcement on the tension side of bending? This is compression, this is tension side of bending. So the reinforcement needs to be provided. Uh, just a second, let me choose another color. The reinforcement needs to be provided on tension side of bending like this. Are you with me?
Yes, sir.
So this reinforcement is in which direction? Along the 4 meter run. So in this slab, I need to provide the reinforcement like this. Happy?
Yes, sir.
And how many such bars should I provide in the width of 1 meter? ऐसे कितने bars मुझे provide करने चाहिए इस 1 meter length में such that their area is the cross section area is 470.41 mm square. Happy?
Yes, sir.
So यहाँ पे मुझे ऐसे bars provide करने पड़ेंगे जिनका total cross section area turns out to be at least 471 mm square. Happy?
Yes, sir.
And so पहले 1000 mm में 470 mm square, then next 1000 mm में another 470 mm square, next 1000 mm में another 470 mm square. So we have to keep this repeating इस direction में. Are you with me?
Yes, sir.
So if you have understood this, now let us talk about what is the minimum steel that IS code says that you should provide in this lab. So if you look at, are you able to see the code?
Yes, sir.
So in slabs, clause number 26.5.2, the minimum reinforcement, this clause is given here. So how much is the minimum reinforcement? So for mild steel reinforcement, the reinforcement in this slab shall not be less than 0.15% of the total cross-sectional area. Are you with me?
Yes, sir.
However, this value can be reduced to 0.12% with high strength deformed bars. So Fe250 is mild steel, Fe415 and Fe500 is star steel or high strength steel. So for our case, this value is 0.12%. Are you with me?
Yes, sir.
So I have taken this value as 0.12%, that is 0.12 upon 100 into what is the total area of this slab? यहाँ पे क्या बोला है देखो, total cross sectional area. So 1000 mm is the width and not 200. I should consider 250 here. Total बोला है ना, it's not effective. Are you with me?
Yes, sir.
So 0.12% of divided by 100 into 1000 into 250. So that turns out to be 300 mm square. Are you with me?
Yes, sir.
So in 1000 mm width, you should provide steel area at least equal to 300 mm square. Is 470.41 mm square greater than 300 mm square?
Yes, sir.
So therefore we can straight away go with this AST. अगर ये value 250 आती, suppose this AST would have turned out to be 250, then we have to provide minimum 300 mm. Are you with me? So greater of the two हमें provide करना है. Happy?
Yes, sir.
So AST minimum, this is greater than AST minimum. Therefore, okay. Therefore, we will go ahead with provision of this area. Are you with me?
Yes, sir.
Now, let me write down the clause for this ASTM. So, which is the clause? 26.5.2.1. So, clause number 26.5.2.1. This is the clause of IS 456. Are you with me?
Yes, sir.
So you have to check that the reinforcement that you require to resist the bending is greater than AST minimum. If it is not so, you have to provide at least AST minimum. Happy?
Yes, sir.
Okay. अब जरा याद ध्यान दो, this AST is provided in which direction along the 4 meter span. Happy?
Yes, sir.
But in slab, you have to also provide steel in this direction. ऐसे. Are you with me?
Yes, sir.
So what is the steel that you will provide in the other direction? As there is no bending in other direction, in that direction we will provide minimum steel. This one. Are you with me?
Yes, sir.
So therefore, this steel will be provided. So AST, let me write down that. AST equal to 470.41 mm square will be provided along 4 मीटर. तो ये स्टील हम कैसे प्रोवाइड करेंगे? अलोंग 4 मीटर. कौन से साइड में? ऑन टेंशन साइड. बट व्हाट इज द टेंशन साइड? बॉटम फेस. सो ऑन बॉटम फेस. Isn't it?
Yes, sir.
So AST is equal to 470.41 mm square will be provided along 4 meter on the bottom face every 1000 mm in every 1000 mm wide strip. इसका मतलब क्या है? तो देखो, हमने स्लैब को कैसे डिजाइन किया है? द स्ट्रिप्स ऑफ 1 मीटर वाइड. तो ये एक स्ट्रिप हुआ, इसके आगे दूसरा स्ट्रिप होगा, इसके आगे तीसरा स्ट्रिप होगा. आर यू विद मी?
Yes, sir.
तो इस 1 मीटर में अलोंग 4000 मीटर ऐसे इस डायरेक्शन में हम कितना एरिया प्रोवाइड करेंगे? 470.41 mm स्क्वायर हर 1000 मीटर, एवरी 1000 mm. आर यू विद मी?
Yes, sir.
राइट. तो ये 1000 mm कौन से डायरेक्शन में मेजर किया गया है? 4 मीटर को परपेंडिकुलर डायरेक्शन. हैप्पी?
Yes, sir.
और दूसरे डायरेक्शन में हम क्या करेंगे? इन अदर डायरेक्शन और इन ऑर्थोगोनल डायरेक्शन AST equal to AST min will be provided perpendicular to 4 meter span in every 1000 mm strip along the span. इसका मतलब क्या है मैं बताता हूँ आप. Are you with me?
Yes, sir.
So in other direction मतलब कौन सा? ये वाला स्टील. हैप्पी? ये वाला स्टील.
Yes.
हाँ, तो हम क्या करेंगे अब? along this is 4 meter. So along this 4 meter we will make a strips of 1000 mm wide. और हर एक 1000 mm में इस डायरेक्शन में कितना स्टील प्रोवाइड करेंगे हम? 300 mm स्क्वायर. आर यू विथ मी?
Yes, sir.
So design steel will be along 4 meter run and that will be 470 mm square per 1000 mm run. एंड दूसरा जो स्टील है उसको हम बोलते हैं डिस्ट्रीब्यूशन स्टील. क्या बोलेंगे इस स्टील को? डिस्ट्रीब्यूशन स्टील. आर यू विथ मी?
Yes, sir.
Steel. This will be provided in the direction perpendicular to 4 meter run. 4 मीटर को परपेंडिकुलर मतलब इस डायरेक्शन में ऐसे ऐसे वो स्टील प्रोवाइड करेंगे. कौन से फेस पे? बॉटम फेस पे. आर यू विथ मी?
Yes, sir.
So this is also provided at the bottom face. Are you with me?
Yes, sir.
So let me demonstrate this through few images. हाँ, तो देखो Are you able to see this one way slab?
Yes, sir.
तो इसमें देखो, there is a beam on one side that is called as support 1. There is a beam on other side that is called as support 2. Happy?
Yes, sir.
This slab is going to bend between support 1 and support 2. तो उसके corresponding जो steel है वो support 1 to support 2 इस direction में होगा. देखो ये steel दिखाया है. Are you able to see this steel? Are you able to see my arrow?
Yes, sir.
हाँ. तो this steel is the design steel. Whereas in this direction, ये जो आपको स्टील दिख रहा है उसके परपेंडिकुलर डायरेक्शन में, उस डायरेक्शन में स्लैब बेंड हो ही नहीं रही है. आर यू विद मी?
Yes, sir.
हाउएवर अगर ये मेन स्टील वाले बार्स आप ऐसे ही रख दे तो दे विल बल्ज आउट ऑफ द स्लैब. तो वो ना हो इसलिए हम इस डायरेक्शन में भी स्टील प्रोवाइड करते हैं और इस जंक्शन पे बाइंडिंग वायर से उसको कनेक्ट करते हैं. आर यू विद मी?
Yes, sir.
सो इट इज सीन लाइक ए वोवन फैब्रिक. हम फैब्रिक कैसे दिखता है वैसे ही रेनफोर्समेंट दिखेगा. आर यू विद मी?
Yes, sir.
तो ये जो रेनफोर्समेंट है पैरेलल टू द सपोर्ट्स के डायरेक्शन में, इसको हम बोलेंगे डिस्ट्रीब्यूशन स्टील. और ये जो रेनफोर्समेंट है अक्रॉस द सपोर्ट्स, परपेंडिकुलर टू सपोर्ट्स, इसको हम बोलेंगे मेन रेनफोर्समेंट. आर यू विद मी?
Yes, sir.
एंड बोथ आर प्रोवाइडेड एट द बॉटम फेस और एट द टेंशन फेस. जहां पे टेंशन आ रहा है वहां पे प्रोवाइड करेंगे. आर यू विद मी?
Yes, sir.
ओके. हाँ. नाउ we will understand the concept of now how do I provide this 470.41 mm square steel is the question. Are you with me?
Yes, sir.
So let me take view YY. So let me call this as view YY. Are you with me?
Yes, sir.
So let me see that view. So how does that view look like? So view YY looks something like this. This is a cut line. The view YY, that means I'm looking from this side. Are you with me?
Yes, sir.
So I'm going to see in fact the beam depth, but the slab is present only up to this extent here. So I'm going to see that view something like this. So this is the beam, and the slab is present only up to this extent. This dotted line corresponds to the slab on the inner side of the beam. Happy?
Yes, sir.
So let me say that this is beam and this is slab. Happy?
Yes, sir.
And in this view, ये 1 meter कैसे दिखेगा? So let me show that 1 meter as well in this view. That 1 meter will be seen something like this. This is 1 meter. Happy?
Yes, sir.
So I consider this slab to be made up of the strips of 1 meter wide. ऐसे 1 meter wide के strips चलते जाएंगे इस direction में. Happy?
Yes, sir.
And how much is the steel that we should provide? AST 470.1 mm square. Are you with me?
Yes, sir.
तो आप जरा इस स्ट्रिप पे फोकस करो 1 मीटर के. इस 1 मीटर में मुझे कितना स्टील प्रोवाइड करना है? 470.41 mm स्क्वायर. तो समझो I have bars provided like this. Happy?
Yes, sir.
And I have not drawn it to the scale, but you have to understand the spacing between two bars is same. Are you with me?
Yes, sir.
So let me call this as the spacing. Happy?
Yes, sir.
So number of bars in 1000 mm width, let me say they are 1, 2, 3, 4 here. So that 4 number is n. So n is, what is n? N is number of bars in 1000 mm strip. Happy?
Yes, sir.
Even it is a half bar, I have to count. You can see that this bar only half is there in this strip, half is there on the other strip. Similarly, this bar, half is there in this strip, half is there outside it. Isn't it?
Yes, sir.
So let me say that there are n number of bars provided in 1 meter. So can you tell me how many gaps or how many spacings will be there if there are n number of bars? तो यहाँ पे कितने बार है 1 2 3 4. So how many spacings are there? 1 2 and 3, isn't it?
Yes, sir.
Are you with me?
Yes, sir.
Okay. And uh, what is the area of steel that lies in 1 meter wide strip? तो ये bars कितने हैं बताओ मुझे? N. Are you with me?
Yes, sir.
हाँ तो और spacings कितने हैं? 1 2 3. Happy?
Yes, sir.
So how do I compute the number of bars? So 1000 divided by spacing. अगर मैं ये करता हूँ 1000 divided by spacing plus 1 will be the number of bars that are there in 1000 mm wide strip, isn't it? For example, let me give you an example. If the spacing is 250 mm, हाँ तो ये हुआ पहला लाइन और ये हुआ लास्ट वाला लाइन. Are you with me?
Yes, sir.
These are the lines, and this is 1000. Happy? If the spacing is 250, the spacing is कितना है 250 है. तो can I mark the lines at 250? देखो ये पहला बार, उसके बाद this is next bar 250, isn't it? उसके बाद का बार that is at 250. उसके बाद वाला बार is at 250. So 253 जा कितना होता है बोलो? 750. And 254 जा 1000, isn't it?
Yes, sir.
हाँ so अगर 250 स्पेसिंग है तो नंबर ऑफ बार्स कितने हैं? 1 2 3 4 और 5. हैप्पी?
Yes, sir.
सो 1000 डिवाइडेड बाय स्पेसिंग प्लस 1, इतने बार्स होते हैं कि नहीं?
Yes, sir.
हाँ सो 1000 divided by s plus 1, these many number of bars will be there in 1000 mm wide strip. Happy?
Yes, sir.
लेकिन इसमें से आधा बार जाएगा इस स्ट्रिप में, इस 1 मीटर में, इसमें से आधा बार जाएगा इस स्ट्रिप में. So therefore I have to subtract 1, isn't it?
Yes, sir.
So what is the area of steel that you are going to provide in 1000 mm strip? Is it 1000 divided by s? 1000 divided by s, these many number of bars into pi by 4 into bar diameter square. Happy?
Yes, sir.
Are we right? Let us calculate it. 1000 divided by s कितना हुआ? 4. हाँ इस केस में तो 4 multiplied by pi by 4 into 5 square. तो क्या देखो ये 3 complete bars है, then ये आधा बार और ये आधा बार. So what is the total area of steel? It is equivalent to area of 4 bars, isn't it?
Yes, sir.
But how much do we want this? 1000 देखो divided by s into pi by 4 of pi square. This we want it to be 470. कितना है वो? बोलो. 470.41 mm square, isn't it?
Yes, sir.
So now let us select the bar diameter. So let me select, I'm going to use the bar diameter of 10 mm. So phi is equal to 10 mm. So in this case, can you tell me what is the spacing? क्या होना चाहिए? 1000 divided by s into pi by 4 into 10 square must be equal to 470.41 square. So what will be the value of s? So let me calculate that. The s will go on the other side. So it will be 1000 divided by 470.41 multiplied by pi by 4 into 10 square. So the spacing turns out to be 166 mm, 0.66 mm. Are you with me?
Yes, sir.
And multiply and round it off on the lower side. If you round it off the spacing on lower side, you are providing more steel. If you round it off on higher side, you are providing less steel. So therefore, round it off on lower side in the multiples of 10 mm. So what are we going to provide? We are going to provide 10 mm dia bars, 10 mm phi bars at the center to center spacing of 160 mm center to center. These bars are provided along 4-meter run. Happy?
Yes, sir.
And in the perpendicular direction, what are the bars that we are going to provide? So in perpendicular direction, what is the requirement of steel? Instead of 470.41, we want the steel which is equal to 300 mm square. Isn't it? 300 mm square.
Yes, sir.
So therefore, what will be the spacing in other direction? So यही formula हम use करेंगे. Same formula is to be used. Only the thing is we have to now replace 470 by 300. Happy?
Yes, sir.
So replace this by 300. Can you tell me what is the value of spacing? Thousand divided by 300 into pi by 4 into 10 square. So that turns out to be 261. So 260 mm is the spacing. Are you with me?
Yes, sir.
So 10 mm at 260 mm, 260 mm center to center. Uh, Perpendicular to this is the sign for perpendicular. So perpendicular to 4-meter run. ये steel हम provide करेंगे. Are you with me?
Yes, sir.
So now let me draw the top view of this slab where I will show this steel. Happy?
Yes, sir.
So this is the slab and the slab continues here. So there is a cut line here. It continues here. The span of the slab is, so I have, if I look from the top, I will not be able to see the beam, but this edge from top, I have to show it as a dotted line, so that I have shown. So these are the two beams. Are you able to imagine this? When I look from the top, I won't be able to see these edges, but they are present inside. Therefore, those are to be shown as dotted lines. Happy?
Yes, sir.
So what are these? What do these dotted lines represent? Inner edges of inner faces of the beams on the two opposite sides edges. Happy?
Yes, sir.
So which direction is 4 meter? The distance between two beams is 4 meters. So this is 4 meter. Happy?
Yes, sir.
So 10 mm and both these steels are to be provided at bottom face, because bottom face is the tension face. Happy?
Yes, sir.
अब जरा यहाँ ध्यान दो. A- Across the along the 4 meter run, the steel that I'm providing along the 4-meter run will be seen like this, isn't it?
Yes, sir.
And this continues. हाँ, so इस स्टील का डिस्क्रिप्शन हम कैसे लिखेंगे? The description of the steel is written in this fashion. So I show the arrows. What is this steel? तो देखो 4 मीटर के along कौन सा स्टील है? 10 mm. So I'm going to provide 10 mm bar diameter, 10 mm phi. What is the spacing? दो consecutive bars में center to center distance कितना है? 160 mm. Happy?
Yes, sir.
160 mm center to center. And on which face are we providing this? Bottom face. So in bracket we write B. So B stands for bottom. If we are providing it on top face, we have to write it as capital T. Are you with me?
Yes, sir.
Okay. And now, are we providing steel in other direction as well? Yes. So what is that steel? That steel is distribution steel. What is that steel? So let me draw in other direction, perpendicular to 4 meter. On the bottom face, we are going to provide a steel like this. Are you with me?
Yes, sir.
Ah. And what is the description of that steel? So these are the arrows that I draw. That steel is 10 mm pi. But what is the center to center distance? 260 mm. Are you with me?
Yes, sir.
60 mm. And where am I providing it? At bottom. Happy?
Yes, sir.
Okay. Now you have to be careful about the spacings that you get. The spacing, the highest spacing that is allowed is lesser of the two. तो मैं वो किससे कम होना चाहिए वो बताता हूँ. So as per IS code, this spacing that which we get 160 mm यहाँ मिला और यहाँ 260, it has to be less than. This has to be less than the spacing S has to be less than 300 mm. Are you with me?
Yes, sir.
And it has to be less than 3 times the effective depth. So 3 times D. So what is 3 times D? 600 mm. So is the spacing 160 less than 300 mm? Yes. Is it less than 600 mm? Yes. So you can go ahead with the spacing of 160 mm center to center. Are you with me?
Yes, sir.
Okay, so this covers the reinforcement detailing. So now only one step is pending in slab design. That is the last step, and that is called as shear check. Are you with me?
Yes, sir.
So step 4, check for shear. So you already know what this similar to beam. We have to give this check. So what do we calculate for this? So we calculate something called as tau V D. So design shear stress. Are you with me?
Yes, sir.
So what is the uh, tau VD design shear stress? So that is VUD divided by the cross sectional area. So how much is the cross sectional area of this slab? Tell me. 1000 into 200. 200 is the effective depth. Are you with me?
Yes, sir.
So this is in mm. This is in mm. So this is in mm square. So tau VD is VUD. VUD is to be substituted now in Newton because I am substituting these in mm square so that I get the stress in Newton per mm square, which is MPa. So what is the value of VUD? बताओ क्या है? Did we compute VUD value? Yes, that is 38.5. No, not 38.5. That is 33.46 kilonewton. Are you with me?
Yes, sir.
So 33.46 kilonewton is 33.46 into 10 power 3 Newton. This divided by, in bracket, 1000 into 200. Happy?
Yes, sir.
So how much is this value? So let me write down this value equal to 33.46 into 10 power 3 divided by 1000 divided by 200. That gives me, this value is 0.16, isn't it?
Yes, sir.
1673 MPa. What do we do next? Then we compute something called as tau C max as per the IS code. So let me go to the IS code. ये हमने already beam के लिए किया है, so I'm not going to explain much. This we have done this process. So shear. We have to go to page number 73. One minute. Are you able to see table 9, table 20?
Yes, sir.
So I hope it is readable. So maximum shear stress, that is tau C max. It is given for different grades of concrete, which is the grade that we have chosen, M20. So what is the value? For M20, the value is 2.8 Newton per mm square. Are you with me?
Yes, sir.
So let me write down this value. This is equal to 2.8 Newton per mm square. ये कहाँ से मिला हमें? This we have got it from table 20 of IS 456 2000. Are you with me?
Yes, sir.
IS 456 table 20 of IS 456. Now, is tau VD that we calculate, that we have calculated, less than tau C max?
Yes, sir.
So therefore it is okay. This tau VD cannot be greater than tau C max. If it is greater than tau C max, we have to revise the depth. We have to increase the depth. Are you with me? So I will
Yes,
write
sir.
tau VD is less than tau C max. Therefore, okay. Are you with me?
Yes, sir.
अब हम क्या चेक करेंगे? Now we will go to table 19 and we will find out how much shear stress can be resisted by the slab with the bottom reinforcement without provision of shear reinforcement. तो हम देखेंगे कि स्लैब को shear reinforcement लगेगा या नहीं लगेगा. स्लैब में हम shear reinforcement typically provide नहीं करते क्योंकि उसकी जरूरत नहीं होती. That's the only thing that we are going to prove here, that we don't require the additional reinforcement. तो उसके लिए क्या करना पड़ेगा? हमें दिखाना पड़ेगा कि डिजाइन shear strength given by 19 है, टेबल 19, वो भी टाउ वीडी से ज्यादा है. सो टाउ वीडी उससे कम होने के वजह से हमें एडिशनल शेयर एनफोर्समेंट देने की जरूरत नहीं है. ये हम प्रूव करेंगे. आर यू विद मी?
Yes, sir.
तो इसमें जरा देखो कौन से कॉलम है. तो फर्स्ट कॉलम इज 100 AS by BD, so that is nothing but the percentage of steel. So now can I calculate the percentage of tension steel in this slab? So can I calculate 100 AS by BD? The answer is yes. कैसे कैलकुलेट करेंगे हम? 100 है, 100 तो वैसे के वैसे रखेंगे. AS तो हमने 1000 mm वाइड इसमें कितना स्टील प्रोवाइड किया है जरा बताओ मुझे. 470, isn't it?
Yes, sir.
हाँ, तो हमने 470 से जो स्पेसिंग आया उसको लोअर साइड पे राउंड ऑफ किया, इसका मतलब है हमने थोड़ा सा 470 से ज्यादा स्टील प्रोवाइड किया है। सो एक्चुअल वैल्यू लेनी चाहिए बट कम से कम 470 तो है ही है। सो देयरफॉर वी विल कंसीडर दिस वैल्यू एज 470। आर यू विद मी?
Yes, sir.
सो 470 पॉइंट समथिंग था, 0.41, तो इतना तो हमने प्रोवाइड किया ही है। आर यू विद मी?
Yes, sir.
एंड डिवाइडेड बाय BD, तो B कितना है 1000 और D कितना है 200। So how much is 100 AS by BD? So let me calculate this value. So it is 100 into 470.41 divided by 1000 divided by 200. So that turns out to be 0.23. Are you with me?
Yes, sir.
So this is 0.23. Let us go back to table 19. So we are going to refer which table of IS code? Table 19 of IS 456 2000. So let me go there. ना 0.23 ये वैल्यू है ही नहीं, 0.15 है, उसके बाद 0.25 है, पर इसके बीच में 0.23 है, क्लोजर टू 0.25, isn't it?
Yes, sir.
And which grade of concrete are we using? M20. So M20 के लिए 0.25 के करस्पॉन्डिंग वैल्यू है 0.36, 0.15 की करस्पॉन्डिंग वैल्यू है 0.28, सो 0.23 के करस्पॉन्डिंग वैल्यू होगी 0.34। आर यू विथ मी?
Yes, sir.
So that is the value of design shear strength of concrete. तो टाउ सी की वैल्यू कितनी है? 0.34 MPa टाउ सी। So in last class I have told you what is in beams. Last class I have told you what is meaning of tau c. Let me also write down that value meaning here. Tau c is the shear stress, shear stress that concrete can resist with flexure reinforcement, but without shear reinforcement. तो shear reinforcement के बिना लेकिन फ्लेक्सर reinforcement के साथ जो shear stress concrete resist कर सकता है, that is tau c. तो इसका मतलब है हमने जो बार्स प्रोवाइड किए नीचे ये वाले 10 mm at 160 mm सेंटर टू सेंटर, उनके साथ लेकिन एडिशनल shear reinforcement प्रोवाइड किए बिना कितना shear stress रेजिस्ट हो सकता है? 0.34 MPa इतना। लेकिन shear stress उसको कितना रेजिस्ट करना है? टाउ VD जितना। टाउ VD कितना है? 0.16। इज इट लेस देन 0.34?
Yes.
So tau VD, the design shear stress that the section has to resist, is less than tau C. What is the consequence? No shear reinforcement is required. Are you with me?
Yes, sir.
So as I said, in this lab we do not provide the shear reinforcement, we just give the check for shear. So this completes the design of one-way slab. Are you with me?
Yes, sir.
Now in tomorrow's class we will cover design of two-way slab, and in day after tomorrow's class we are going to cover design of short column. तो ये दो लेक्चर्स अभी होंगे कल और परसों। हैप्पी?
Yes, sir.
Okay, so let us stop for today.